Right. Hi everyone, nice to meet you guys. So today I will just cover the most basic of species distribution models. I think this is a type of very useful models, and actually I think when you look at the last 20 years of the development of this kind of models and other models, you can see in the future the ultimate distribution models and the ultimate population models and community models will be the same model. So in the past, like I don't know, maybe 50 years ago, the traditional way to do things is to either look at the distributions of species and ignore the dynamics of that distribution. So people only look at one snapshot of 1 year data or the average of several years data. But on the other hand, we have population dynamics models that people look at this total population size and how this total population size change over years and ignore the spatial distributions. So that's two aspects of the one thing, but in the past, people study them separately, and it seems most plant people work on the distribution models, most animal people work on the population dynamics models. But in the last 10 to 20 years, Mao and Mao models have been developed, and you can see these two kinds of models are developed toward the same directions. I think at some point they will become the same model. And at that point, I think, anyone who need to use some ecological models need to at least know something about species distribution models. That's why I think this is a very important topic, but also very basic. And there are tons of new papers coming out every day. So there's no way to cover all of them. So I can cover the most basic things. So what are species distribution models? I will just use this from this paper. These two authors wrote this review, and in their paper say the species distribution models are models that are used to study two things, either the occurrence or the abundance of species. Although occurrence is more like a simplified version of abundance. So you have this area and you have some numbers of these species. You could have 1, 2, and a number, but you can also have 0, which means that species is not there in the area. So when it's 0, we say it's absence, and 1 is any number from 1 to any large number, that's presence. So if you have abundance data, you can easily change the abundance data to presence, absence, or occurrence there. But species distribution models also link that observation of occurrence or abundance with environmental data, particularly since now we often have environmental data for the entire study area or for the entire world, and at very fine spatial resolution thanks to GIS techniques. So when we link the species distribution with environmental data, first we gain understanding about the relationship between species distribution and environment. That's the first thing these models will do to gain ecological and evolutionary insights. So basically to gain some kind of understanding. And based on that understanding, we can make predictions. So these are two important things species distribution models can do for us, and they are related. And by that I mean, if you want to make predictions, you first want to have some understanding. You don't want to just use a numeric relationship to make predictions without knowing what that numeric relationship really mean in the ecosystem. So again, for these species distribution models, we have two basic components. First is the observation of the species, either as occurrence or abundance, and also the environmental data. That's two basic components. And for the use of species distributions, it's first to gain understanding, and second, to make predictions. And those two uses are related. So how many types of species distribution models are there? If we look at the statistical forms of species distribution models, basically any statistical models can be used to understand and predict species distributions. So, but for statistical models, we have the basic frequentist approaches, we have Bayesian, we also have machine learning. So all those can be used as species distribution models. And if we look at the type of response variables, as I said, it can be either the occurrence of species or abundance of the species. Although in some cases, people don't really distinguish the observation and the true occurrence if people believe their observations are perfect. So, and if they collect Qing data and they think the Qing data is perfect to represent abundance, they can also call it abundance or Qing data. But there are a bunch of species distribution models that account for imperfect detection in model structure. And in that case, people tend to call the observations or their data either presence or absence or count, and call the true but latent status occurrence or abundance. But here sometimes I will not really distinguish them, because today I will talk about two kinds of models. And one kind of model, people normally consider their observations as perfect, to be perfect, and in the other model, they don't. So, and we can also look at the number of response variables. If there is only one response variable, that means you only have observation for one species, that's a single species model. But sometimes you can have data for more than one species. However, your response variable is just for one species, and your data for other species are used in the model as predictors. So in that case, you have multiple species, but you can only look at unidirectional interspecific interactions, such as how species B influence species A. But in that case, you won't be able to look at how A influences B. And there are also models with two or more response variables, and obvious that's a situation where you look at multiple species, and you can depend on the model, you can look at interspecific similarity, but you can also look at unidirectional interspecific interactions. For example, you can test if the interaction between species A and species B is strong or not, but you don't really know the direction of that interaction. You can also incorporate bidirectional interactions in your model, which means you are looking at the influence of A on B and the influence of B on A simultaneously. And also, I think the most basic species distribution models does not consider temporal processes as aside the traditional ways to look at the data for 1 year or average observation over several years. So in that way, your model is static, which means it does not include temporal processes. But of course, recent development allows us to look at the temporal processes, and those are dynamic models. We can also see if spatial processes are represented in these models. But of course, any species distribution models have some spatial information in it, right? That's why you can look at the distribution. But except the most basic spatial information, we can also look at spatial autocorrelation between your spatial units, and we can also explicitly incorporate spatial processes such as immigration and emigration in model structures, but those are very advanced and complicated models. So as a side, any statistical models can be used to study species distributions, and the most basic is just old frequentist models, and two basic ones. First, if we want to look at the occurrence of a species, we can simply use logistic regression, right? So why is your observation the occurrence or the presence absence of a species? So in this area, you see that species in that area don't. And that 0-1 data follows a Bernoulli distribution with this probability pi. So I don't have any index here, but you can consider this index by space. And this pi is for the function of your covariates. So that's a basic form of a logit regression. Or if you have count data or abundance data, that count can follow a Poisson distribution, and with this parameter lambda, and log lambda can be x times beta. So yeah, if you have that, you can already build a link between your observation of your target species and the environmental covariates. That's the first thing, right? The explanation. Then if your environmental covariates X cover the entire study area, you can use that relationship to predict species distribution for the entire area. So understanding and prediction, you can have both, sure. And that makes it a species distribution model, but except that there is no real power or the special things in any of these models. I don't, at least that's my impression. I don't see any people who is still using this kind of models. in literature, but these are the most basic forms of species distribution models. And based on that, we can make the model more complicated to account for more interesting stuff. And one interesting stuff we want to look at is nonlinear relationship. But we also have the machine learning and the Bayesian approaches. So the machine learning approach is better to detect nonlinear relationship because it's almost automatic. So you put in data, the machine learning approach will figure out that nonlinear relationship for you, so that is very convenient. If you want to use Bayesian approach or the frequentist, you basically need to determine a bunch of nonlinear relationships yourself. Then you use some model selection approaches to select one or a few best ones, although there are some limits of those things. But on the other hand, as I said, most time our observations of either the occurrence or abundance are not perfect. So there is some observation error there. If you want to explicitly account for that in your model structure, then the Bayesian approach will be more appropriate, and it's not really easy to account for observation error in machine learning approaches. So the machine learning approach and the Bayesian models are two ways to expand and improve the most basic frequentist approach, but they have their own power and limit. And of course, there are new studies to kind of combine the powers of these two approaches, such as Bayesian non-parametric models, such as Bayesian artificial neural network kind of thing. But in general, these two approaches have their power and limit. So today, I actually want to use a very simple example. We will look at occurrence data. We will only look at one species, and we will only look at 1 year's data. So that means the model will be static, and we won't incorporate things like spatial autocorrelation. And of course, for static model, we cannot incorporate things like immigration and emigration explicitly in the model. So you may ask, oh, you look at such a simple case, so what will we get from that? But even for a very simple case, we can look at two things. And the first is a nonlinear relationship between your observation and the covariates. Second is the observation error. However, as I said, machine learning approaches are better than Bayesian approaches in dealing with nonlinear relationship, and it's the other way for the observation error. So today I will introduce approach, or you can say it's my thinking to kind of to combine the strong points of these two types of approaches without using very complicated modeling techniques. Okay. So that's why today I will talk about two different approaches. First is called this multivariate adaptive regression spline, or MARS. And this is a non-parametric or semi-parametric approach that is very good in detecting nonlinear relationship. On the other hand, I will also talk about occupancy models. And the occupancy models are good because they can account for detection probability explicitly in their model structure. And I want to kind of combine the strengths of both. So first, for the Mars, it's developed by Friedman, and that's the paper first introduced this approach. And the basic idea is that if you have a bunch of data, here you have y and x, right? You can see some relationship here. But if you just use a simple linear regression to find a fitted line for these two variables, you can see that's a fitted line. But obviously, this fitted line is not very good, because if you look upon, you can see kind of this shape, right? So when x is small, most of the points are below this line, and when x is large, also most points are below this line, but in the middle, most points are above the line. So obviously, there is some nonlinear relationship that a simple linear regression cannot grasp. And if you use a Mars, this machine learning approach is very smart. It will figure out several values in x, and next it will fit a straight segment in each interval. But not only the segment will be the best fitted line for the points in that interval, but also those segments will be connected. So the approach itself will figure out all those things for you, and eventually you can see the shape of this right line represents some nonlinear relationship. So you really don't need to figure out those things yourself. The machine learning approach will learn that and tell you. So it's very convenient. And on the other hand, occupancy model, I think the most basic occupancy model is developed by Mackenzie and colleagues and published in this paper. So it's a hierarchical Bayesian model. So it's not that good in detecting nonlinear relationship, but as a hierarchical Bayesian model, this model actually includes an observation model and a process model. So it kind of separates the observation from the true ecological process. So in that way, the relationship between in this process will be more accurate. So this model, first, again, you will have some observation. And here, I will use the word presence absence, because this is kind of model in which we want to distinguish observed presence absence with the true but latent occurrence. So why is the presence absence? So it's either 0 or 1. For any site I, you can go there and repeat the observation for ji times. And we assume that during those replicates, the true but latent status z did not change. So if the species is there, it's always there during that period of time, but you just observe it for several times. So say if z is 1, that means the species is there. But when you go to observe it for say 3 times, you may have, your data may look like 101, which means in the first time and third time, you observe this species. And in the second time, you missed it, even though the species was there. So you can see that's why Z is not indexed. Mm-hmm.
So just to confirm, right, what this is asking is, if I'm looking for a particular species and I go to some part of the forest and I don't find that species, it could have been that I didn't find that species because it never exists there, or it could exist there and I just happened to not see it.
Yes.
Or it not be there in that moment in time.
You're right.
So this is how you account for whether or not your failure to observe the species was because it doesn't exist in one place, or you just didn't see it, but it could exist there.
Right. Okay. And this is the most basic form. So basically, we'll only consider false negative. We don't consider false positive. So that means we only consider the situation that the species is there, but we didn't see it. We don't consider the situation that the species is now there, but we see or we think we see it. So you can see in this observation model, Z is either 0 or 1. So when it's 0, that means the species is now there. Then you can see the first part becomes 0. So in that case, Y is always 0, no matter what J is, no matter what P is, because Z is 0, right? So regardless of the value of P, Z times P will be 0. So that means when the species is not there, you always record absence or a 0 there. But when Z is 1, which means the species is there, the detection probability will be just P, which means you have a probability to detect it and record a 1. But you also have a probability of 1 minus P to miss that species and record a 0. And this true but latent status Z, as I said, it has value 0, 1. So obviously, it can follow a Bernoulli distribution with pi, and then logic pi is a function of your covariates. So that will be that. But as I said, this model is not very, at least it's not very convenient to detect any nonlinear relationships. So for the case study, I will look at this beetle species in Alberta, Canada, and I will relate its occurrence with temperature and forest cover, and I will also predict its distribution. So you can see this is a study area, and I have covariates, temperature, and forest cover. I have covariates for everywhere in the study area, but for these great dark ponds, that's the ponds I record the presence or absence of that species. So I really didn't go to there. I don't know if it's there or not. Even for the ponds I have observation, if I record a 0, that doesn't mean the species is not there. There is still a chance species is there, but I just missed it. So I just want to use this data set to first gain some understanding about the relationship between this species and these two covariates, and also to predict its distribution in this entire area. So that's data I load. Here we'll have some R code. I load that data. Then I use a high function to look at the first 3 rows. You can see during this short period of time, not me, but the observer went there and make 4 observations. So in the first row, he didn't see that species in all the 4 opportunities. And in the third row, he observed the species there every time, which means the species is there, right? But when I look at the second row, you can see he only observed the species in the second time. Remember that we think or we assume the occurrence, the true occurrence of that species did not change among these 4 observations. So when you observe it in any of the opportunity, that means the species is there. And obviously, the observer missed that species in 3 of the 4 times, which means the observation is not perfect. But then the question is, for the first row, is the species there or not, right? Even you didn't see it in all the 4 times, there is still a chance the species was there, but you just missed it in all the 4 times. So, okay. Also, I have the covariates for each side. So for the non-linear relationship, you can see if I only consider linear and additive relationship, since I only have 2 covariates, right? So I only have 3 models. The first model, I only include temperature. The second model, I only include forest. And the third model, I include the additive form. However, if I start to consider some nonlinear relationship, such as a quadratic form, you can see I immediately have more models here I need to consider, and I don't even consider interactions between these 2 variables yet. And if I start to consider both the interaction and the quadratic form, I will have more models. So you can see originally I only have 3, but now have 12, right? And I don't even consider other nonlinear relationship. I only consider a quadratic form, but there can be many other relationships we don't know. So you can see when you consider the, Sorry, you can finish it. Okay, when you consider the nonlinear and interactions among variables, you immediately have much more candidate models. And if you want to use something like AIC to do model selection, that can be very time consuming. And if you use non-parametric, it can be done in 1 step. I will show you. Yes.
So does this slide relate to mass function? I've been confusing what you talked before about mass that you fit or just to find a nonlinear relation, right?
Yes.
So this is the same thing that you do with Mars?
No. Mars will give you some kind of trend. You don't really know what kind of parametric form you need to use to represent trend. But if you are familiar with like quadratic form or log or other kind of nonlinear relationships, you can find something to represent that. So in the Mars, there is no this thing. It only connects a bunch of straight segments together to represent some kind of linear relationship. But with that thing, you can come up with some nonlinear relationship too. Yeah, maybe when we look at the case, that will help you to understand. But this is not for Mars, because this is still parametric. Mars is a non-parametric approach.
So real quick, the difference between parametric and non-parametric is, for a parametric model, you're explicitly stating what the form of the model looks like.
Yes.
So here, for one of these models, you're explicitly stating that you're going to have this temperature squared term or this forest squared term.
Yes.
And by in a non-parametric model, you're not making any assumptions about the form of the model. Is that correct?
Yes,
okay.
That's right.
Does that make sense for everybody? Yep.
Okay, next I will just use this library called Earth. But first thing, since for the Mars model, I don't really use these 4 columns. Instead, I want to combine those into one kind of occurrence observation. So what I do is that if the sum of this 4 is 0, then this last one will be 0. Otherwise, it will be 1. So which means if you observe the species in any of the opportunities, then we will think it's there. And if you don't observe it in all the opportunities, we think it's not there. And we believe, we assume this for the last column, that's a truth, although obvious it's not, but we will see how bad it could be, or how good it could be. So here I use this Earth function. Basically, this is a function in the Earth library to run Mars. I have two models. You can see that here, the first part is kind of a formula. If you are familiar with linear model or generalized linear model, it's just this formula. This y01 is a function of these two covariates, and the data used is called data. And since my observation is 0, 1, I choose a family to be binomial. That's for current data. And this degree equals 1 means that I only consider additive relationships, but the model will figure out some non-linear pattern for me. And I also do a 20-fold cross-validation here. For the second one, the only thing I change is to let degree equals 2, which means I will consider level 1 interactions. And here I only need to consider level 1 interaction because I only have 2 covariates. So next I have, okay, also I save the results as feed 1 and feed 2. Remember that I don't have a bunch of different models fitted. As I showed, if I want to consider all those relationships, I have 12 models. I don't have 12, I only have 2. One consider interactions, and the first one doesn't. And the nonlinear relationship will be detected by the model automatically. And when I compare the AUC value of this, you can see that the one that considers the interaction between temperature and forest has overall higher AUC value than the additive model, which means the interaction is important. So basically this part will give you the AUC value for the additive model. This will give you the AUC value for the interactive model. So feed 2, for example, here is the output of the second model, and you have this dollar sign. You can take out one of the output in feed 2. I pull them together, called AUC. Then I use a box plot to create this box plot with some options. But the idea is just to create this box plot.
Real quick, is everybody familiar with what Qing means by interactions? Right. Should we explain that? Yes? No? Basically what he's saying is, for the first model, where he just says, I think he set some factor to 1, he's only looking at elevation and force as potential explanatory covariates. But when he adds the two-way interactions, that says the model, it tells the model to look at temperature and forest, and also temperature times forest. So an interaction between those two things, as well as, I think, temperature times temperature, which is that squared sort of nonlinear pattern, and forest times forest. Does it do that?
No.
No, it just
the square term is taken care of automatically by the model. So okay. The model will give you something like a quadratic form or even more complicated relationship, even if you only consider additive relationships.
Okay, I see. So yes. the two-way additive relationship is including that temperature times forest
yes.
interaction.
Yes. So later I'll have a graph that may be useful for you to. Yeah, I also use this command to look at the better model, the interactive model, and to see if how important these two variables are. And it seems temperature is more important, but since we have the interaction from there, and also the forest is also important. It's just a little bit less important than temperature. So that tells us that we need both variables there. But we still don't know what kind of nonlinear relationships we want to, we learn from that, right? So I have some code basically for, since forest is a value from 0 to 1, so I use this forest high-low, so it's either 0, which means the lowest value the forest variable can take, or 1, the highest value the forest variable can take. And I predict some response variable. So X predict is kind of the fake covariates there, and I use a predict function here. So the object is best model, the second one, and the fake covariates is X predict. And since we have this logit link function, we have inverse logit. And eventually, when we predict the y values, I plot the y values, the predicted y values against these fake covariates. But I have values for forest equals 0, and another set of values for forest equals 1. I think that's a loop here. So eventually we have these lines that tells us that there might be a quadratic form there between the occupancy and temperature. And that quadratic form can be different when forest is low, like the red line, or forest is high, like a blue line. So basically, if we use Mars, right, but we let degree equals 1, which means we only consider additive form, we don't consider the interaction, Mars can give you something like this, like one of the lines to show you some nonlinear relationship, but these two lines will be parallel if we don't have interaction, which means the blue line should be higher than the red line or lower than the red line, but the difference between the blue line and the red line should be a constant everywhere. So that means you kind of just shift the red line above or lower. But since we have the interaction here, and these two lines, you can see they have different shapes, although both shapes represent some kind of quadratic form. So that's very convenient, because if you want to detect this using parametric approach, it can take you a while, and you don't really detect this if you didn't include this as one of the candidate model in your model side. But on the other hand, something weird can happen, like this thing here. That's a thing of a non-parametric approach. Sometimes this approaches not only Mars, but other non-parametric approaches like artificial neural network, random forest. They are not very good at distinguish pattern and noise. So when we do this, we want to detect the pattern. We want to learn about the pattern and kind of filter out the noise. We don't care about noise, right? But sometimes, like something like this, it might be just some noise, because you really don't have a good way to explain this, why the probability increase there and decrease a little bit, then increase again. That doesn't even make sense, right? But this kind of non-parametric models cannot prevent that. That's a downside. But the good thing is that it's very convenient to detect this kind of nonlinear relationship for you because it's very fast. You only need to write 2 models instead of 12 to get that.
Any questions on this figure?
Good. Okay, so at this point, we learned a lot of things from the Mars. We know that an interaction between temperature and forest is needed in the model because the fit2 model is better than fit1 model based on the AUC values. And by looking at the graph in the previous slide, we can say a quadratic form is needed for the temperature. Doesn't look like any other kind of non-linear relationship, right? If you have other kind of, it probably won't look like this. Although you need to be very familiar with the shape of different kind of non-linear forms to get that from the figure. So, however, we still don't account for observation error in our model. We just consider, if we didn't see the species, we just assume that it's not there, although that could be wrong. So the next, I will use the occupancy model. So to do that, I use the unmarked package. And so for the unmarked package, so the form is a little bit different. This unmarked data. So first, I need to prepare the data for the function I need to use later. So I use this unmarked frame occupancy. So the first part is your observation. This time we use the original 4 columns. Remember the first?
I just have a question. Are you going to go through the 40 slides?
Yes.
There's numerous slides at the end that are just suggested.
Yes, there are some. Probably I can be a little bit faster for those. But overall, the observation, we use the original observations. That's the first 4 columns in our data. Then we have those covariates. We don't have any observation covariates here. We will assume that the observation probability is a constant. That's an assumption of the original occupancy model, but obviously you can extend that. Then we use this form. So it still looks like a formula of similar to like linear model, but here you don't need to specify your response variable because in the last step, you already have this y equals data 1 to 4. So that will be the response variable. So when you use this unmarked data, the function knows what the response variable is, but it doesn't know what kind of form of the covariates you want to use. As I said, we learned that we want to incorporate the quadratic form of temperature, and we also want to consider the interactions between temperature and forest. That's why I write the formula like this. I think the first one is for, this part is for the observation covariates, so that's a constant. And yes, and also some other options to tell the function that we only assume false negative, but not false positive. So here, if you don't have the Mars, and if you want to consider this kind of complicated non-linear relationship, you need to write 12 models from the simple list. So I think the simple list is that for this part, from here to the end of the line, you only have temperature. and you can only have forest, and you can have temperature plus forest. You can have temperature times forest, but that doesn't include the quadratic form. So if you want to include everything, you need to have 12 models instead of 1. You need to run all those, then you need to use like AIC to compare those, which is it's okay, but you know, with a non-parametric model, we detect these nonlinear interactive relationships, so we don't really need to bother to write so many models. So to summarize the result, remember that I saved the result as this feed object, and just summary it. You can see the estimates of everything here, and also the detection probability thing. So first, okay, remember this estimates of detection probability is at the largest scale. So first, I need to calculate the detection probability for each opportunity. Remember, we have 4 opportunities, right? So for each one, it's about 50%. It's not that high. You have half chance to miss that species. But remember that we have 4 opportunities. So the chance to observe the species in at least one of the opportunities is calculated as this. So you can see that chance is really high. It's 93%. So that's really good. That means the observed detection, non-detection is very close to the truth. That gives us confidence that the Mars model works well and gives us some reasonable results. So that's one thing. You can use the parametric occupancy model's result to kind of to evaluate your result of the non-parametric approach, right? If this ground observation probability is low, then your mask is probably really bad. But at this point, since this value is really high, we can be confident about the result of Mars. Next, I make predictions. Remember that for the Mars, I only use this simple command predict to predict the response variables, just because it's not parametric. Everything is in this black box, and the code will do that for me. But for the parametric approach, we need to write down the formula here and to make that prediction. But the result will be similar. That's still a predicted response curve. So it looks like this. If you remember the other graph, actually they are very similar. But this time you can see we don't have those little nodes here or there. It's a pure trend, so we can be very confident that this is the pattern we want to see, right? And there is no nodes there. So I think both approach in this case works well. One's a little bit good at this, the other one's a little bit better at that. But overall, since the detection probability, the ground detection probability is high, so both approaches will give us really good results, and they are actually very consistent with each other. You can see that. And with these relationships, I predict the occurrence probability for the entire study area. So here I load some data for the covariates for the entire study area. Then I make predictions. You can see I use a formula here, and to make the graph, I also change the scale from 1 to 10 by using this line of code. Then I can use these heat colors here to make graph, you can see that's a predicted distribution occurrence probability of that species. You can see the area with high probability of occurrence and low probability of occurrence.
So this is how you go with just data on temperature in forest and then some point observations, how you can extrapolate to the entire area.
Yes.
Right. So
Yes.
Dark red spots are a higher probability that the lion beetle species occurs there.
Yes.
Yellow and white are both.
Yes. Yes. These are based on the information of covariates. Basically based on this relationship here. You just use this relationship to predict this. Okay, so from the occupancy model, we can estimate detection probability, and then we see even the detection probability for each survey is not very high, about 50%. The grand total detection probability is actually very high. That can give us more confidence about the Mars, but also we use the relationship learned from Mars in this model. That saves us a lot of time, and we estimate parameters to represent that nonlinear interactive relationship, and I use that relationship to make predictions. So both models can do something for us, and I think it's a better way to combine the strengths of both. So as I said, that's the most basic thing. And if you are interested in this kind of models, first, there is this R package to ensemble a whole bunch of non-parametric approaches such as GAM and Mars, we just introduced, and like random forest, Maxent, and support vector machines. So by using this package, you will get relationship response curves for all these approaches, and also kind of average them to give you more confidence about your results. Because one model can be wrong, right? But if you use all the, I don't know how many are there, but if you use all of them and most of them agree with each other, that will give you more confidence.
Question.
Mm-hmm.
So have you used the Mars in Biomod 2?
I didn't. I forgot the package I used before, but at some point I found the Earth package. I found it's very convenient because not only it can implement Mars, but it allow you to choose different families, like the binomial for presence absence data, person for count data. So that's very convenient. So from that part, I just use that package.
Right.
I believe there are tons of packages out there.
So the reason not to use Mars is because of that convenience or because of other thing else?
I think you can always try to use Mars, but I think the concern is that if the overall detection probability is low, then your result of Mars is not very reliable. Although to know that detection probability, you need to use some parametric approaches. Another thing is just that small noise there, but that's not just about Mars, it's about any non-parametric approaches. But I think some people think it's no big deal. Some people are more sensitive about that. I'm not like a Bayesian guy, so I'm not a huge fan of non-parametric approaches. So I will say that small noise really bugs me. But some people may say it's nothing. Let's just use that kind of thing. So it's sometimes the choice is more like a personal preference than some real reason, or it's more like which one you are more familiar with. But it's a good thing to know both and know their strengths and limits. Also, there are multi-species models. And I want to be really quick about this part, and if you're interested, you can just read it and to find the paper. But these are all parametric approaches. So really, if you want to extend the model to include more species or to include spatial autocorrelation, and even some more advanced things like the dynamic, the temporal processes, and also even the spatially explicit dynamic models, the non-parametric approaches are not very good, are not very flexible to make those extensions. But on the other hand, it's very easy to extend your model to incorporate something you want to incorporate, you want to consider in the model structure by using the Bayesian approach. Because for the Bayesian approach, you can basically include anything you want. Whenever you find a distribution or a math formula for that thing, you can just put it there. So that's it. Thank you.